So you're welcome once more to this YouTube channel at Best Science Brain YouTube channel. Today we're going to take a look at chemical thermodynamics, a topic meant for those in first year of higher institutions and for those that are doing A-level courses in chemistry. So this is your online moderator, Dr. B. Our focus today will be on first law of thermodynamics, internal energy, work done on the chemical system or work done by a chemical system. We're going to briefly look at second law of thermodynamics and then other things that are important, hence law and other aspects of this topic, mainly for first year students. So today we're going to start by defining chemical thermodynamics. So what is chemical thermodynamics? So chemical thermodynamics, by definition, is the branch of physical chemistry which deals with heat and other forms of energy, such as work, in relation to chemical reactions and physical changes occurring in a system. So that's a brief way of defining chemical thermodynamics. We say the branch of physical chemistry which deals with heat and other forms of energy such as work, relationship or relation to chemical reactions and physical changes occurring in a chemical system. So that is how to define chemical thermodynamics. Now in thermodynamics, we are concerned mainly with four quantities. So we are concerned with four major quantities in thermodynamics, and those quantities include internal energy, enthalpy, entropy, and Gibbs-free energy. So the major four variables we concern with in thermodynamics is internal energy, U, which is the sum of the total energy, the total kinetic and potential energy of atoms or molecules in a chemical system. So that's the first quantity we are concerned with, internal energy, the sum of the total kinetic and potential energy of atoms or molecules in a system. And we present this internal energy with the symbol U. It's conventional to use U to represent internal energy, while some people use the symbol E, capital E. And that factor we are concerned with is enthalpy. Enthalpy. The symbol of enthalpy is H in chemistry. Enthalpy defined as it is the sum of internal energy and the product of pressure and volume of a system. Enthalpy is the sum of internal energy and the product of pressure and volume. So we can say enthalpy of a system again by H equal to U plus PV. The sum of the internal energy and the product of pressure and volume of a system. That is what is meant by enthalpy of a system. The next factor we are concerned with in this study is entropy. Entropy. So what is entropy? In chemistry, Entropy is represented using the symbol capital S. Entropy, this is the degree of randomness or disorderliness of a chemical system. So how random or how disordered a chemical system is known as the entropy, symbol S. And the fourth factor is what we call the Gibbs free energy. The Gibbs energy, G, discovered by a man called Ernest Gibbs. Gibbs free energy. So G, the symbol is capital G. So is it the energy available for doing work in a thermodynamic system? So in thermodynamics, we are concerned with four major factors or properties of the system, which include internal energy, which is the total energy of atoms or molecules in the system. This energy can be potential, like vibration energy, or kinetic energy. We're also concerned with enthalpy, which is the sum of the internal energy and the product pressure and volume. Enthalpy can also be defined as total heat content of a system at constant pressure. Then we also have entropy, which is the degree of randomness or disorderliness of a chemical system. We are still concerned with Gibbs free energy, with the energy available for doing work in a chemical system or in a thermodynamic system. So at this point, we're going to look at what is meant by a chemical system. So a chemical system, as you have it on the board, is a specific set of chemicals, or it could be reactions or conditions that are being studied or observed in a confined space. For instance, when I put a chemical inside a container, a particular chemical can be a single chemical in a container or a gas in a container cylinder. So the chemical and the container or the gas and the cylinder make up a chemical system, even though no reaction is taking place there. And then when I add two gases or two chemicals in a container and they are reacting, so that will also form a chemical system. So a chemical system, there must not be a reaction. It can be a container which contains a gas or a chemical in it. So the container, the gas, and the walls of the container and the surrounding environment where the container is placed make up a chemical system. Or perhaps I have two substances reacting in a container or in a vessel. That will also make up a chemical system. So when we talk about system, even the universe we are is a system where we find ourselves. The universe with people or the people living in it make up the system. In biology, we talk about the ecosystem, which consists of the living things in the environment. So, but now we're talking about a laboratory setting whereby you have a container or a vessel for a reaction. Could be a beaker, could be a conical flask, could be a crucible, or whatever container you want to perform a chemical reaction, or where you place a chemical substance. So that substance and whatever laboratory environment where it is placed, perhaps it's placed on the laboratory table, perhaps it's placed in the cupboard, that becomes a chemical system for you. So the system consists of the component, the substances in the container, whether they are reacting or not, the container and the walls of the container, the boundary, and then the environment, which could be the laboratory or the surrounding where the substance is kept. That's the chemical system. Now we'll go to types of chemical system. What are the types of chemical system we have? We have what's called a closed system. So what do I mean by closed system? Or let me start with closed system is okay. So this is a system in which matter is constant, but energy is exchanged with the surroundings. That's a closed system. For instance, let's assume that I have a container where I'm heating calcium carbonate. It has a crucible. And you know that when you heat this substance, it breaks down to calcium oxide and CO2. If I seal this container, seal it very well so that no substance leaks to the outside and nothing comes in, matter remains constant. But because the walls of the container can be permeable due to tiny holes, energy can be exchanged from outside, and energy can go in and also move out. So energy can leave in form of heat and also enter because the walls could be permeable. So this kind of system where the substances are retained, nothing goes out, nothing comes in, is sealed, is called, but energy can be exchanged with the surrounding, is called a closed system. Then the other type of system is called open system. So what is an open system? So this is a system in which both matter and energy are exchanged with the surroundings. So both matter and energy are exchanged with the surroundings. For instance, they still use the crucible, we use heating calcium carbonate in it, and it's left open without sealing the cover. So this type of system is an open system because the substances, which maybe one of them is the product, one of them is gaseous, will diffuse out and escape from the container. And energy is also exchanged between the outside and the inside of the container. So we call this an open system. So the next type of system is called isolated system. In chemistry, closed and open system are more practicable. So we always come across closed and open system. Why? Isolated system is mainly used in theory. It's not all that practicable. So it's a system in which matter and energy remain constant. That means in this kind of system, matter is not exchanged with the surroundings. Energy is also not exchanged with the surroundings. So matter and energy remain constant. Example is a perfectly sealed thermoflask. A thermoflask perfectly insulated or perfectly sealed or insulated thermoflask can function as an isolated system where it retains water to a particular temperature without absorbing heat or losing heat. That can be taken as an isolated system. So having done that, move to the next thing. So now we're looking at properties of a chemical system. So we itemize some properties of a chemical system on the board. The first is temperature. Temperature refers to the measure of the average kinetic energy of molecules in a body. So it's the measure of the average kinetic energy of molecules in a system. So that is what we call temperature. The measure of the average kinetic energy of molecules in a system, which can also be called the degree of coldness or hotness of an object. The next property of a chemical system is energy, which is the capacity to do work. The next property is entropy, which we had defined before, the degree of randomness or disorderliness of chemical system. The next property of a system is enthalpy, which is defined before as the sum of the internal energy and the product of pressure and volume. The next property is pressure of a system, which is the force per unit area. And then volume, with the space occupied by substances in a system. So these are the properties of the chemical system. Having done that, we're going to look at these properties can be divided into two variables or two functions. The one we call state function and the one we call path function. So the property of a system can be divided into two functions, state functions and path functions. So as I said, we have the properties of a system can be divided into two functions or two variables. We have the state function and the path function. State function says the property of a system whose value does not depend on the path taken to reach its specific value. They are also called point functions. So state functions are also called point functions, and they include pressure, temperature, volume, mass, internal energy, Gibbs free energy, entropy, and enthalpy. These are called state functions. The properties of a system whose value does not depend on the path taken to reach their specific values. We'll now move to path functions. Path function, these are properties of a system whose values depend on the path taken to get between states. These are properties of a system whose values depend on the path taken to get between states. Examples of path functions, the two major examples are work and heat. Work and heat are path functions. So having done that, we'll now move to the first law of thermodynamics. So the first law of thermodynamics states that the energy change in an isolated system must be zero. Remember that an isolated system is a system whereby matter and energy is constant, so there's no energy change. So energy change in an isolated system must be zero. Or you can still put it this way: energy can neither be created nor destroyed, but can change from one form to another. I repeat, it states that the energy change in an isolated system must be zero, or energy can neither be created nor destroyed, but change from one form to another. So this is the first law of thermodynamics. Now, under this first law, we are concerned with an important equation derived from the first law of thermodynamics. A very important equation which says delta U equal to Q minus W. So this is a very important equation that governs the first law of thermodynamics. So that delta U is nothing but change in internal energy. At the early part of this video, I defined what I mean by internal energy. I said internal energy is nothing but the total energy of molecules or atoms in the chemical system. And this energy will include kinetic and potential energy of particles in the chemical system. That is the internal energy. So the change, this signifies change. That means UF minus UI. That means, what does it mean? UF means the final internal energy minus the initial internal energy. So that means of the change. So Q is nothing but the quantity of heat energy transferred in the system. And you know that heat is a form of energy. So heat is a form of energy transfer that occurs between a system and its surroundings. So heat is a form of energy transfer. which occurs between a system and its surroundings. And you know that heat flows from a region of higher temperature to region of lower temperature. Heat flows from region of higher temperature to a region of low temperature. So heat is measured in joules since it's also energy. And then W stands for work. W stands for work. So that is the formula we're going to be concerned with in the first law of thermodynamics. Now, looking at heat, quantity of heat in the body. So the quantity of heat absorbed or given out by a body can be calculated using the formula MC, change in temperature. So find the amount of heat in an object which an object loses or gains. We use that formula. Where M is the mass of the body or of the object. C is the property of the body called the specific heat capacity of the object, which is a constant. And then the change in this theta means temperature is now final temperature minus initial temperature. So let's take a question with respect to that. So let's look at this question that says 250 ml of water was heated from 10 degrees Celsius to 90 degrees Celsius. Calculate the quantity of heat energy supplied to the water. In bracket, you have specific heat capacity of water as 4.2 joule per gram per Kelvin. So you look at this question, we are given the volume of water 250 ml. So let's write as VH2O, 250 milliliter. And then the initial temperature of water as 10 degree. The final temperature of water as 90 degrees. So the change in temperature becomes the final minus initial, which is 90 minus 10, which is 80 degrees. So having done that, we're given also the value of the specific capacity of water, which is 4.2 joule per gram per Kelvin. To find the heat supplied to the water, we're going to apply the formula MC, change in temperature. So you look at the board, every other thing is given to us. We're given every value there except mass. We have our C, we have our change in temperature. What we have is volume. We don't have the mass of water. So how do we find the mass of the water? To find the mass of the water, we have to convert this volume to mass. So the volume of water is given as 250 ml. And 250 ml is the same thing as 250 cm cube because 1 milliliter is equal to 1 centimeter cube. Density is given by mass over volume. So density given by mass over volume, we make mass the subject since we want to find the mass of water. So mass becomes density times volume. And the density of water is constant. The density of water is 1.0 gram per cm cube. So the density of water. So mass now becomes density 1.0 gram per cm cube times volume, which is 250 cm cube. And you know that per cm cube, the negative sign also means over cm cube. So it's the same thing as that. So cm cube cancels cm cube. We now multiply 250 by 1. The mass of water is 250 grams. So having obtained the mass of water, we can go ahead to calculate the heat supplied to the water. Heat supplied to the water by the formula is MC, change in temperature. That is going to be, the mass is 250. The change in temperature is 80. And the value of C is 4.2. So when we solve and get our final answer becomes 84,000 joules of heat energy supplied to the water, 84,000, or in standard form, 8.4 times 10 to the power 4 joules. So that is the amount of heat that was supplied to the water. So that is it. So that's the concept of heat. Next, look at some questions that involve the first law of thermodynamics. So let's look at this question that says, if a chemical system absorbs 500 joules of heat and does 300 joules of work on the surroundings, calculate the change in internal energy of the system. So look at this question. The heat absorbed, which is Q, is for heat, is 500 joules. Then the work done is 300 joules. We're looking for the change in internal energy. For the first law of thermodynamics, we stated earlier on in this video, our change in energy begin by W, work minus heat. So you substitute, which is you substitute and then solve. You begin by, there's an error here, you begin by Q minus W, sorry. So you substitute, our Q is 500, our W is 300, that gives us 200 joules. So the change in internal energy is 200 joules for this question. We'll take another problem. So another problem on the board says, if a system does 150 joules of work during an adiabatic process or expansion, what is the change in internal energy? So look at this question. The work done is 150 joules. Let's itemize what's given to us. We're looking for the change in internal energy. And the process is said to be adiabatic. Adiabatic means that the heat, quantity of heat is zero. So adiabatic process means no heat exchange. So it's a thermodynamic process in which there's no heat exchange. So that is what is meant by adiabatic process. So in such processes, the quantity of heat becomes zero. So solving this problem now, we apply the law, the equation for first law that says change internal energy again by Q minus W. So since it's a adiabatic process, Q is 0, we now have 0 minus the work 150. So the change in energy becomes minus 150 joules, negative 150, since our Q is 0. So you see, that's why the answer is negative. So now we'll move over to a very important aspect of the first law of thermodynamics, which is work. We already talked about heat. We already talked about internal energy. Now we are talking about work. Work refers to the energy transferred when a force is applied over a distance. So work can be obtained using, in your elementary physics, as force times distance. F is force and S is distance. So unit of force is taken as Newton, distance as meter, giving you the joule. So work is taken as force times distance. But in chemical thermodynamics, work results from volume changes, such as when a gas expands or contracts. So in chemical thermodynamics, we are not making use of force and distance to calculate work, although that's the basic concept of work. In chemical thermodynamics, we're talking about work done mainly when a gas expands or when a gas contracts. For a gas to expand, you're going to exert pressure on the container or on the piston and push it up. And for a gas to contract, the pressure will now be exerted on the gas and the walls of the container, pushing the piston down. So in chemical thermodynamics, work can be defined by the formula negative pressure, the S means external pressure times change in volume. So the two equations boil down to the same thing. So look at this equation. How does this equation explain work? This second equation and these two, are they equal? They are equal because pressure is obtained by force over area in physics or physical chemistry, and force is Newton, area is meter square. That gives you Newton per meter square, which is what call a Pascal. So the unit of pressure is Newton per meter squared or Pascal. And volume, unit of volume is meter cube, the standard unit of volume. So if I multiply these two units, pressure times volume, the unit of pressure is Newton per meter squared. Volume is meter cube. When I multiply the two units, I'm going to have Newton per meter squared. I can add the power since they have the same base. Minus 2 plus 3, that gives you Newton meter, the same as you have there, which is joules. So work is also pressure times change in volume, apart from using force times distance. So that means this is a correct formula for finding work as well. Now, in chemical thermodynamics, we talk about two kinds of work when a gas is involved. We talk about a positive work and negative work, depending on whether it's a work of expansion of gas or work of compression of a gas. So let's start with one of them. So let's look at the first type of work done on a gaseous system, which is the work of expansion. So let's assume that this is the initial volume of the gas in the container, and this is a piston, a movable piston. So the initial volume is V1. So as the gas expands, you're going to push this piston up to get a new volume V2. Now, in this situation, when we have work of expansion, a gas expanding, lifting the piston up, we now say that work is done by the system to its surroundings. Work is done by the system to its surroundings. The change in volume here becomes V2 minus V1. And of course, you see that V2 is higher than V1. That means the change in volume will now become positive value. Positive. Or will be change in volume should be greater than 0 because V2 is higher than V1. So this is work done by the system to its surroundings. Now, when work is done by the system to its surroundings, we say that work is negative. We say that work is negative. Why do we say that work is negative? Because the system is doing work against the external pressure. The system is doing work. Against the external pressure. So that's why work done is said to be negative. You look at the formula for work, where you have work negative P and then delta V. So if delta V is positive, as we said, if you substitute the value of delta V here, the work will still become negative. So when a gas is expanding, the piston is being pushed up. The change in volume becomes more than 0 or positive. We say that work done by the system is in the negative work because the system is doing work against the external pressure and the system is losing heat energy. We say we have a negative work. So the next we're going to consider is work of compression. So the next we look at is work of compression, not expansion. We'll now say this one is work done on the system. Remember that work of expansion is work done by the system, while this is work done on the system. So you want to compress a gas. Let's say this cylinder is filled with a gas. Volume is V1. To compress means to push the piston. You push the piston downwards. When you push the piston downward, the volume of the gas now becomes smaller, compacted or contracted. So the final volume now is less than the initial volume. The change in volume, which should be final minus initial, becomes negative value, or the change in volume is now less than 0. In this situation now, we'll now say that work is done by the system and work is positive. We now have a positive work. Why do we say we have a positive work? Because the system is now gaining energy. We have a positive work done. From the formula we have, where we have work is negative It's pressure times external pressure times volume. So if this is negative now, you substitute the negative value here. You made this one minus times minus will give you positive work. So in work of expansion of a gas, work done by the system, work done by is negative. Work of compression of a gas, work done on the system is a positive work. So let's look at this calculation. A cylinder filled with a gas initially has 2000 joules of internal energy. So this is the initial internal energy, which is 2000 joules. 500 joules of energy is transferred into the cylinder as heat. So 500 represents our heat Q. And the internal energy increases to 2200. So the final internal energy is 2200 joules. Calculate number one, the change in the internal energy. So let's start the first one. The change in internal energy given by final internal energy minus initial internal energy, which is going to be 2200 minus 2000, and that gives us 200 joules. And the change in internal energy. Number two question says, how much work was done on or by the gas? How much work was done on or by the gas? So let's write the upper side. So you know that the change in internal energy given by Q minus work done. So that is it. We're looking for work. So make substitution. Our change in energy is 200. The quantity of heat is 500 minus W. So make W the subject of the formula. So we cross over 200 minus 500, what minus W. So minus 300 is equal to W. Is equal to minus W. So minus cancels both sides. W becomes equal to 300 joules. Now, since W is 300 joules, positive answer, what do we say now? Since it's positive, now say work is done on the system. So work is done on the system because this is the work of compression. Because when work is done on the system, we have a positive value. So work is done on the system. So let's look at this question that says a gas is contained in a piston and the initial volume of the gas is 2.0 meter cube. The gas is compressed to a final volume of 1.50 meter cube and the external pressure acting on the gas is 1.0 atmosphere. The system absorbs 400 joules of heat from the surroundings. Calculate the work done on the system and the change in internal energy. There are two questions here, and change in internal energy. So we're looking for two things, work done and change in internal energy. So let's this what is provided for us. We have the initial volume of the system, our VI, 2.0 meter cube. Our final volume, which is 1.50 meter cube. The external pressure, P external, 1.0 atmospheres. Then heat absorbed, 400 joules. I think that is all we need, or all that is provided for us in the equation. We have all these quantities: initial volume 2.0, final volume 1.5, external pressure as 1 atmosphere, heat absorbed 400 joules. So let's work up. Let's wipe the upper part of the board. So the first thing we're looking for is the work done. Work done begin by minus P external times change in volume. So the change in volume is obtained using final volume minus initial volume. So final is 1.5, initial is 2. We have negative 0.5 meter cube. Why they change negative? Because the gas is compressed from a higher volume to a smaller volume. So I'll have a negative change in volume. So we apply this formula. But before we apply this formula, the pressure is given to us in atmosphere. The volume is given to you in standard unit, meter cube. So you have to convert this pressure to a standard unit. So that's why you're given in bracket. 1 atmosphere is equal to 1.0 to the power 5 pascals, which is the standard unit of pressure. So the pressure in atmosphere, 1 atmosphere is equal to 1.01 power 5 pascals converted. So you see that. Having done that, we now find the work done. The work done becomes equal to negative 1.01 power 5 pascal, that's the pressure, times negative 0.5, which is the change in pressure. So when we solve this, our final answer becomes 5.05 times 10 power 4 joules, because the work done is now in joules. So minus will give you positive answer. So it's a positive work because the system is being compressed. Then we have to find the change in internal energy. Change in internal energy given by quantity of heat minus work done. So that is the formula for change from the first law of thermodynamics. So having done that, the quantity of heat supplied is 400 joules. That becomes 400 minus 5.05 power 4. So that is it. When we solve this, our final answer becomes negative 50 100 joules. This is the change in internal energy for this system. So take another problem on the board that says a gas in a cylinder expands from an initial volume of 3.0 meter cube to a final volume of 5.0 meter cube. The external pressure acting on the gas is 2.0 atmosphere and the system loses 600 joules of heat to the surroundings. Calculate the work done and the change in internal energy. In bracket, 1 atmosphere is equal to 1.01 times power 5 pascals. Looking at this question, this is what we have. The initial volume is 3.0 meter cube. The final volume is 5.0 meter cube. The external pressure, PES, is 2 atmosphere. We'll convert to the standard unit, multiply 2 by 1.0 times power 5 in pascals. That gives us 2.02 power 5 pascals. And the heat lost is 600 joules of heat energy. So the first question we are asked to do is to find the work done by the system. So I want to write the upper side. To find the work done by the system, we'll start by first of all finding the change in volume. So the change in volume becomes final volume minus initial volume, which is 5 minus 3. So in this case, now the change in volume is positive, unlike the previous one, which was negative. The previous one was negative because the gas was being compressed. But this one, because the gas is expanding from a smaller volume to a bigger volume, the piston is going up. So that is 2 positive. So the work done is given by P, negative P external pressure times change in volume. So the external pressure is 2.02 power 5, then times 2. Work done becomes negative 4.04 to the power 5 joules. So this is the work done by the system. Then the next question says we should find the change in internal energy. So the change in internal energy can be obtained using delta U equal to Q minus work done. Q minus work done, and Q is the heat. So the quantity of heat given to us in the equation is 600 minus the work is negative. So you can see that negative sign appearing 2 times, minus here and then this carry minus. So the change in energy becomes 600 minus will give you plus 4.04 power 5. So when you solve this, your answer becomes a positive answer, which is 404 40 4600. So 404,600 joules is the change in internal energy for this system. So we'll take one more problem on this. Look at this problem on the board that says how much work is done by 0.54 mole of a gas that has an initial volume of 8 liters and expands under 30 degrees Celsius and 1.3 atmospheres. The number of moles is 0.54 mole given to in the equation of the gas. The initial volume is 8 liters. Temperature is 30. You convert it to Kelvin by adding 273. That gives you 303 Kelvin. Pressure in atmosphere is 1.3 atmosphere. Now, to find work done, we either think of using this formula Q minus W, or this formula, we find the one that is convenient for us to use in this question. So the first formula, internal energy equal to heat minus work, cannot be used because the internal energy was not given to us and the heat was not given to us. So we can use the second formula because we have a pressure and we can find change in volume. But the problem here is that to find the change in volume, we have to look for the difference between the initial and the final volume. So what was given to us was the initial volume. The initial volume, we don't have the final volume. So how to calculate the final volume of the gas? So we have the ideal gas constant to R. So find the final volume, we use the ideal gas equation PV equal to nRT. V becomes nRT over P. So you make your substitution. Your N is 0.54. I use my R as 0.0821. My temperature as 303. My pressure as 1.3. So somebody may wonder, why didn't I convert the pressure to Pascal? Because if you look at the unit of the constant given to you, atmosphere reflects this pressure, liter reflects the volume, mole reflects this, Kelvin reflects temperature. So no need to convert because they are all in uniform. So you don't convert to pascals. So when you solve the volume, you're going to obtain, after evaluating that, the volume is going to be 10.33 liters. 10.33 liters as our volume. Having obtained the final volume, we can now calculate our change in volume. Our change in volume becomes VF minus VI. The VF is 10.33. The VI is 8. That gives you 2.33 liters. Now, we want to work in SI unit because the work we are looking for should be in joules. So the standard unit of volume is a meter cube. So convert to meter cube by dividing by 1000 or multiply by power minus 3. So that is in meter cube. Divide by 1000 or multiply by 3 to the power minus 3. The next is to convert this pressure to SI or standard unit. So pressure is 1.3 atmosphere. Multiply it by 101,325. That is 1 atmosphere equal to 101,325 Pascal, given to us in bracket. And that gives us 131,722.5 pascals. So that's the correct value in pascals. So, having done that, we'll now look for work. The work done on this system now will now become W equal to negative external pressure times change in volume, which is negative 131,722.5 times 2.33 times 6 power minus 3, because it must be in the standard unit. So when we multiply that out, we have approximately negative 303 joules. So why is this work negative? It means that the gas is expanding. That's the system is doing work to the surroundings. So that is it. So at this session, we're looking at the thermodynamic processes. There are three major thermodynamic processes. The first is called isothermal process. Second is called adiabatic process, and the third is called isochoric process. So these are three major thermodynamic processes, and each of these processes, one of the thermodynamic factors, either temperature, heat, or volume, is kept constant. So isothermal process means this is a process where the temperature of the system remains constant throughout the process. So any process where temperature remains unchanged or remains constant is said to be isothermal. Iso means the same temperature. Iso, the same temperature. So since temperature is constant, internal energy does not change. So when temperature is constant, the internal energy does not change. The value of U remains constant. So irreversible work done in isothermal process. So when you have an isothermal process, the work done on the system again by the formula W equal to nRT. That N is the number of moles of the gas, R is the gas constant, T is the temperature in Kelvin. Then Ln is natural log of Vf over Vi, final volume of the gas over initial volume of the gas. So let's take a question here. So let's look at this question under isothermal process. It says 2 moles of ideal gas expands from a volume of 1 liter to 3 liters at a constant temperature of 300 Kelvin. Calculate the work done by the gas, and the value of R is 8.34. The gas constant is R, 8.34. 314 joule per mole in standard unit, 8.314 joule per mole per Kelvin. So we're looking for work done. If you look at this question, at constant, look at the language, constant temperature, this phrase, that means isothermal. That is, temperature is being constant. So the work done in isothermal condition given by W equal to nRT lean, natural log, or the final volume of the gas divided by the initial volume of the gas. If I go on to work on this, I'm going to modify this equation. I don't wish to work on natural log. I want to work on log to base 10. And as I told you in the previous topics, I told that the natural log of a number is equal to 2.303 log of that number. So log to base 10 of that number. So I'm going to replace this with this. And I have V W equal to nRT multiplied by 2.303 log Vf over V. I'm replacing natural log with this, since this is the equivalent. So I can work with log to base 10. So solving that, what do? We'll get the values given to us. The number of moles is 2 moles, N is 2 moles. The change in volume, the volume of the gas. Okay, the final volume is 3 liters. Initial volume is 1 liter. 1 to 3. The temperature is not relevant for the equation. We're not going to use temperature because at constant temperature, we don't. Okay, it's relevant. It's there. Sorry, it's 300 Kelvin. Okay, it's relevant. It's given to us in Kelvin. So then the gas constant is 8.314 in SI unit. So having obtained all the values we need, we can write the upper side and then use this formula here and make a substitution like this one. W becomes equal to number of moles of the gas is 2. The gas constant is 8.314. Then the temperature value in Kelvin is 300 multiplied by, open a bracket, 2.303 log Final volume 3 liters over 1 liter. Liter cancels liter. So I now have work equal to 2 times 8.314 times 300 times, open the bracket, 2.303 times log 3. Or 3 over 1 is 3. So find log of 3. So log 3 will give us 0.4771. So we'll continue working. Our work becomes 2 times 8.314 times 300 times 2.303 times 0.4771. So the work of 10 is going to be 5,473. 5,473.8 joules. So that the work of 10 from that system. So we have treated the first thermodynamic process, which we call the isothermal process, in which we say that in such process, temperature remains constant. The next isothermal thermodynamic process is called adiabatic process. In this process, there is no heat exchange with the surroundings. In this process, the quantity of heat is zero. There is no heat exchange for the surroundings. Remember the first law that says the change in internal energy given by quantity of heat minus work done. So for an adiabatic process, if Q is zero, it means that delta U equal to 0 minus W. That means our change in internal energy becomes equal to the negative work for an adiabatic process. So we go to the next process called isochoric process, which is also known as isovolumetric process. So isovolumetric, that is the same volume, constant volume. So this is one where the volume of the system remains constant in the process. So in an isochoric process, volume is constant, and in such process, no work is done. Why did I say no work is done in an isochoric process? Because work is pressure times change in volume. So if the volume is 0, that means we now have the pressure times 0. The no change volume, that becomes 0. So in isochoric process, no work is done. So having done that, we go to phase transition. So under phase transition on the board, we are talking about the change of state of matter. Change of state of matter from one state to the other. And of course, there are three major states of matter: solid state, liquid state, and gaseous state. We can still talk about another state that is not all that common, called the plasma state. So looking at solid and liquid and gaseous state, you can see that solid moving to liquid is called melting or fusion. When a solid melts, it requires a heat at the melting point. The point of heat required to change a solid to the liquid at the melting point is called the latent heat of fusion. The latent heat of fusion. That heat is not detected by the thermometer. Just like when ice is melting. If ice is melting, the reading of the thermometer remains at 0 until the melting completes. If a solid has the melting point of 80 degrees, if you heat the solid, the temperature continues to rise until it reaches 80. When it reaches 80, the reading remains constant until it reaches melting. Opposite of melting, that liquid turning to solid, is called vaporization. That is an error. Liquid turning to solid, liquid to solid is called freezing. Correction, freezing or solidification. Solidification or freezing. So you see, the two changes occur at the same temperature for every substance. Then a solid can change to gas, which is called sublimation. Few solids can change to gas. Examples: iodine crystal, ammonium chloride, dry ice. These compounds can change from solid state to gaseous state direct. And the gas can still return back to solid. This is called deposition. Then we move to this aspect. A liquid can change to gas, which is called vaporization. The quantity of heat required to change a liquid to gas at a constant temperature is called latent heat of vaporization. I repeat, the quantity of heat required to change a liquid to gaseous state at a constant temperature is called latent heat of vaporization. That is why when water is boiling, for instance, the temperature of the water remains at 100 degrees, showing that it's changing to gaseous state. When you want to change a solid to a liquid is called latent heat of fusion. Then the opposite, a gas going to liquid, returning back to liquid is called condensation. So this change of states we have on the board is what called a phase transition. During phase transition, the properties of matter can change, or like properties like density, heat capacity, structure of matter can change or do change through phase during phase transition. So on the board, we have a phase change diagram, a plot of temperature against heat energy for a solid heated until it turns to its liquid. So you can see this aspect represents the substance in solid state. When heat is applied, the temperature rises. At this point, the solid is melting. So this place consists of solid and liquid. Because during melting point, some solids must have turned to liquid, while some are still remaining as solid until the end of the melting process. So you see the solid is melting, turning to liquid. While the reverse, liquid turning back to solid is called freezing. You can see the second arrow. The reverse process, liquid returning back to solid is called freezing. So freezing and melting occur at the same temperature for a given substance. For instance, look at water. Ice melt at 0 degrees Celsius, pure ice, while pure water freezes at the same 0 degrees Celsius. Just give an instance. Then after melting, you move to liquid state, and then you heat more, the liquid continues to rise in temperature and it reaches another change of state, which is boiling. At boiling point, you see that it will start going as gas, vaporization. So when the liquid is boiling, it is partially liquid and gas. Some molecules must have escaped, while some molecules are yet to escape as liquid. So vaporization taking place, turning to gas, and the opposite, a gas coming back to liquid, is called condensation. So you see, this is a phase diagram for a solid when it is being heated. A very simple illustration of a phase transition. Then we're going to look at some important points on phase transition, some important points like the critical point, critical and the triple points. So we'll look at three important points which are observed during phase transition. The first is called the critical temperature, TC. So what is critical temperature? It is the highest temperature at which a substance can exist as a liquid. The highest temperature at which a substance can exist as a liquid, no matter how high the pressure is. So the highest temperature at which a substance can exist as a liquid, no matter how high the pressure is. Above this temperature, the substance cannot be liquefied, regardless of the pressure applied. So above the critical temperature, the liquid cannot, the substance or the vapor cannot turn to liquid, no matter how high the pressure applied is. So now go to number 2 point called the critical pressure, PC. So what is critical pressure? This is the pressure required to liquefy a substance at its critical temperature. Remember, as I said, above the critical temperature, the substance cannot be liquefied. But at the critical temperature, it is possible to liquefy the vapor, but above it, you cannot liquefy it. So the pressure required to liquefy a substance at its critical temperature is called the critical pressure. Above this pressure, no distinct liquid and gas phases can exist. Above this pressure, no distinct liquid and gas phases can exist. Then we'll go to the third point, which is called the triple point. This is the temperature and pressure at which the three phases of a substance coexist in equilibrium. This is the temperature and pressure at which the three phases of a substance coexist in equilibrium. So we'll look at Clausius-Crepron equation. Clausius-Crepron equation is an equation that describes the change in vapor pressure with temperature during phase transition. Change in vapor pressure with temperature during phase transition, where P is vapor pressure, R is gas constant, T is temperature in Kelvin, and delta H Vp is the enthalpy of vaporization. So this is the Kraft-Krepron equation, and the C is a constant. So let's consider a liquid having two vapor pressure P1 and P2 at temperature T1 and T2. Let's consider a vapor, at having pressure of P1 and P2 at temperature T1 and T2. So a substance in vapor state having pressure P1 and P2 at temperature T1 and T2 respectively. So with this, we can write for the first condition, natural log of P1 equal to negative H Vp all over R T1 plus C. We call this equation 1. For the second condition, we can say natural log of P2 equal to delta HV all over RT2 plus C, equation 2. So we have formulated two equations for two conditions of substance in a vapor state. The P1, the initial pressure, P2, final pressure, initial temperature T1, and final temperature T2. Then let's subtract equation 2. Equation 1 from 2, there is 2 minus 1. We'll now have natural log of P2 minus log of P1 equal to negative H vapor pressure all over RT2 minus, then minus this all over RT1, then plus C minus C. So C minus C is 0. So what did I do? This minus that, then this minus then that. So the minus sign will now cancel off. We now have natural log of P2 minus natural log of P1 equal to negative H vapor over RT2 plus negative H vapor all over RT1. You can swap and rearrange this. This can also be written as natural log of P2 over P1, bringing them under the same log, equal to, you can have delta H vapor pressure all over RT1 coming in front, pushing this one behind, minus delta H vapor pressure all over RT2. So, having done that, we can now factorize. So factorize the right hand side. So we now have this natural log of P2 over P1 equal to delta H vaporization all over R in bracket opens 1 over T1 minus 1 over T2. So you take the LCM of this side, you now come to P2 over P1 equal to the latent heat of the molar heat of operation over R into T2 minus T1, bringing the two of them under the same denominator, T1 times T2. That is it. So, having done that, we know that log of a number, as I explained initially, you can convert natural log to log to base 10. So log of a number is 2.303. Natural log of a number is equal to 2.30 of log of a number to base 10. So we can change this as 2.303 log P2 over P1 equal to this molar heat of vaporization R T2 minus T1 all over T1 times T2. You can divide both sides with 2.303 and I have log P2 over P1 equal to enthalpy of vaporization all over 2.303 R bracket T2 minus T1 all over T1 times T2. So either this equation, or this one, any of them demonstrates the Clausius-Crepron equation for a substance in gaseous phase, taking the initial and final state into consideration. So let's take two examples on this, two calculations on it. So let's look at this one on the board that says calculate the molar enthalpy of vaporization of pure diethyl ether, which has vapor pressures of 57 millimeter mercury and 534 millimeter mercury at minus 22.5 degrees Celsius and 25 degrees Celsius. So we're going to list what we have here. What are we looking for? We're looking for the molar enthalpy of it. We're looking for delta H vaporization, unknown. So the pressures given to, or the first pressure P1 is 57.0 millimeter mercury. Second pressure P2 is 534 millimeter mercury. The corresponding temperatures T1 that correspond to this is minus 22.5. Add 2 centigrade to it and get it in Kelvin. Our T2 is 25. We add 2 centigrade to it to bring it to Kelvin. That gives you 298 Kelvin. While the first one, minus 22.5 plus 2 centigrade, will give us what value? Will give us, if you calculate, will give us 250.5 Kelvin. So that is it. We have itemized all we need. We can apply the Clausius-Crepron equation that says log P2 over P1 equal to the enthalpy of vaporization all over 2.303 R into T2 minus T1 all over T1 times T2. Have written that, we can move up and make a substitution. We can wipe, our gas constant is already given to us. So our gas constant is 8.314 in standard unit. So we can move up and then make a substitution. We now have log, our P2 is 57, our P1 is 534, making substitution here, equal to the enthalpy of vaporization, unknown, all over 2.303 times gas constant 8.314 in the formula. Then into our T2 is 298, T1 is 250.5 into 298 times 250.5. So we solve. Solving, we now divide, okay, we made an error here, P2 is 534, should be up, while P1 is down, 57. So we divide the left hand side, divide 534 by 57, and that will give us 9.368. Log 9.368 equal to, we now have, we multiply 2.30 like this. We multiply the 2, we're going to have 19.15. 19.15. Then we go to this side, subtract the numerator, 298 minus 250.5, we get 47.5. All over, multiply the denominator, we're going to have 74649. 74649 in closing bracket. So having done that, what we'll now do is we'll now find the log of 9.368. That gives us 0.9716. So we'll now have 0.9716 delta HVAP all over. Then all over, okay, we can multiply this like that. We now have 40, numerator multiply 47.5 delta HVAP all over, multiply the denominator together. We'll have okay, 19.15 times 74649. We can multiply 0.9716 times 19.15 times 74649. If you cross multiply, what you have, that give you 47.5 delta H VAP. So the enthalpy of vaporization will now become 0.9716 times 19.15 times 74649 all over 47.5, making this the form of the variable side by 47.5. The final answer to the question will give you 29240, 29240 joules per mole, or 29.24 joule, kilojoule. So you divide by 1,000, you convert to kilojoule per mole. So this is the enthalpy of vaporization of this question. So I have a question on the board that says a substance has a vapor pressure of 200 millimeter mercury at 60 degrees Celsius. Calculate the vapor pressure at 40 degrees Celsius. Assume that the molar enthalpy of vaporization is 40 kilojoule per mole. Have the gas constant in standard unit in bracket 8.314. So let's start. The pressure, the first pressure given to us is P1, 200 millimeter mercury. Corresponding temperature T1 is 60. Convert to Kelvin by adding this. That gives you 333 Kelvin. Calculate the vapor pressure, looking for P to the higher pressure or the next pressure. At T2, T2 is 40. Convert to Kelvin, that gives you, if you add 313 Kelvin as at T2. They were given the enthalpy of vaporization, delta H VAP, as 40 kilojoule per mole. I'll multiply this 40 by 1,000. Why did I multiply by 1,000? So I can convert it to mole. 1 kilojoule is 1,000. This is in mole. Look at this in joule. This is in kilojoule. The units are not uniform. So either I convert this one to kilojoules by divided by 1,000, divided by 1,000, or multiply by 2 and minus 3. Or you convert this one to joules by multiply by 1, so they become uniform. So our R becomes 8.314 joule per mole per Kelvin. So having done that, we'll put our Clausius Crepon equation that says log P2 over P1 bracket closes equal to delta H VAP all over 2.303 R into T2 minus T1 all over T1 or multiplied by T2. So we can now use this equation to solve this problem. So we'll move up, log P2. So the value of your P2 is what you're looking for, unknown, over P1, log of P1, P1 is 200, over the value of this is 40,000 in the standard value, in joule per mole, all over 2.303 times 8.314 for the gas constant into T2, which is 313 minus T1, 333, all over 313 times 333. So we'll move to solve. So having done that, you will evaluate the, let's look at the question again. But if we evaluate this operation here, 40,000 all over 2.303 multiplied by 8.314, we'll now be getting log P over 200 equal to, if we evaluate that value, those values, we're going to have 2089 approximately, 2089, then subtract, that'll give you minus 20 up, so all over 313 times 333. So we move further. We have now log on the other side, log p, we can separate the log, minus log 200, separating the log, the numbers into different log to base 10. We now evaluate this side. 2089 times, this is times, what that means, the bracket, times minus 20 divided by 313 times 333. When we evaluate the right hand side, we're going to get negative 0.40, negative 0.4008 on this side. So we'll find log of 200. Log of 200 is 2.301. So we have log p minus 2.301 equal to minus 0.4008. That means log p, that becomes minus 0.4008, crossing this to that side, plus 2.301. If I add the two values, I'm going to have 1.9002. So 1.9002. Looking for p. So if log p is 1.9002, and that p is your p2, you know that. That p stands for our p2. So p2 now becomes anti-log. You take the anti-log. You take log on both sides. Anti-log of 1.9002. And the value of our p2 is equivalent to approximately 79.5 millimeter mercury. That is our P2. So we're still taking one more problem on Clausius-Kreplon equation. The equation says a substance has a vapor pressure of 500 millimeter mercury at 80 degrees Celsius. Calculate the temperature at which the vapor pressure is 200 millimeter mercury. Assume the enthalpy operation as 30 kilojoule per mole. The gas constant is given in bracket as 8.314 joule per mole per Kelvin. So let's pick the values given to us. The first pressure there is at P1, 500 millimeter mercury. The first temperature there is T1, 80 R273 to it. That gives you 353 Kelvin. Calculate the second temperature. We're looking for T2. Second pressure is 200 millimeter mercury. Then the enthalpy of vaporization is given to us as 30 kilojoule per mole. Convert to joule, multiply by 1,000. You should know why I converted to joule. I did this kind of thing in the previous example. This is in joule. This is in kilojoules. So I had to make them concord, make them to be the same. So our R is 8.314 joule per mole per Kelvin. So we'll quote our equation, the Clausius-Kreplon equation. That gives you this. That's what you need to solve this. Vaporization VAP. T2 minus T1 all over T1 minus T1 times T2 under. So having quoted the required or necessary equation, we can write the upper side and make our substitution here. So our log P2 is 200. Have log 200 over P1 500 equal to delta HP. Our enthalpy is 30,000 all over 2.303 times 8.314. Then T2 minus T1. The value of T2 is unknown. The value of your T1 is 353 all over 353 times T2, since T2 is unknown. So solving, we have log 200 over 500 give you 0.4 equal to, solving out, we'll solve out this. We have 1566, that is, solve out this 30,000 divided by this denominator, you have 1566.8 into T2 minus 353 all over 353 T2. So having done that, we can find the log of 0.4. Find the log of 0.4. The left hand side will have negative 0.3979 equal to multiply out the numerator, or what I'll do to make it easy, okay, what I'll do is, let's just write this out first. You can expand the numerator if you wish. That is, to expand means multiply this with T2 and also multiply this one with 353. Or you divide both sides. Divide both sides with 1566.8, so that this will vanish from this side. So have minus 0.3979 all over 1566.8 equal to 1566.8 all over the same 1566.8, bracket opens, T2 minus 353 all over 353 T2. So this cancels out. You see that? So having done that, so when we divide the left hand side, we getting, let me wipe the upper side, we getting negative 0.0000254 equal to T2 minus 353 all over 353 T2. You then cross multiply. When you cross multiply, you now have negative 0.00004 times 353 T2 equal to T2 minus 353. So multiply the left hand side. You multiply the left hand side, you're going to get negative 0.089, negative 0.0897897 T2. That's what it's going to give you. Equal to T2 minus 353. Let's collect like terms. So crossing over, I'm going to have negative 0.0897 T2 minus T2, this one moving over, equal to minus 353. So when you subtract negative 0.0897 minus T2, that gives you 1.0897 T2. 972, negative, of course. You're like this value minus, the question here is 1. So minus 0.0897 minus 1 gives you this. Bring down the T2 equal to minus 353. Minus cancels minus. So T2 becomes 353 all over 1.0897. So when you divide, you have your final answer as 324 Kelvin. So 324 Kelvin is our T2. If you wish to express the answer in Celsius, what you do is you subtract 273 from it. That is 324 minus 273. And that will give you 51 degrees Celsius. If you convert to Celsius, that becomes the answer in Celsius. So having done that, move to Henry's law. So at this point, we look at Henry's law of constant heat summation, a very important law in thermodynamics. So Henry's law of constant heat summation, there are different ways of stating it, but they all boil down to the same meaning. So we have a particular method here, a particular statement here for it, which says that if a reaction is the sum of two or more other reactions, the enthalpy change of the overall process must be the sum of the enthalpy changes of the constituent reactions. I repeat, if a reaction is the sum of two or more other reactions, the enthalpy change of the overall process must be the sum of the enthalpy changes of the constituent reactions. So in Hens law, we can have a reaction which is divided into two or more other reactions. What it means is that if we add the two or more other reactions, you get the main reaction. How do you now get the enthalpy of the main reaction? What you do is you add the enthalpy of those constituent reactions, and that will give you the enthalpy of the main reaction. We don't add like that. There are some steps we observe before we start adding the enthalpy of the main of all those constituent reactions, because there should be changes that could be done before we start addition. So let's look at the steps involved in determination of an enthalpy of reaction by using Hens law. We know that Hens law is a very important law in thermodynamics. It's also used to calculate the lattice energy of a substance, which we did when we did chemical bonding under von Haber cycle. We can also use the Hens law to determine the enthalpy of formation, also the enthalpy of combustion or the calorific value of a substance when combusted. So Hens law is important. We're going to apply it now in this tutorial to calculate the enthalpy of formation of reactions and also the enthalpy of combustion of reactions. So let's look at the steps involved when we're about to use Hens law. What do we do before we start adding the enthalpy of the constituent reaction that make up a general or an overall reaction? So look at these steps on the board. Steps involved in the determination of the enthalpy change or heat of a reaction using Hens law. The first step is adjust the known reactions to match the overall reaction by either A, reversing the reaction. This changes the sign of the enthalpy change for the reaction. B, multiplying the reaction by a constant factor. Also, multiplying the enthalpy change by the same factor. So what I mean is this: you have to match the reaction given to you to the overall reaction to see whether the reactants appear on the same side as you have in the main reaction and the products appear on the same side as you have on the main reaction. But if it's opposite, that is, if the reactants on the reaction given to you is on the product side of the main reaction, that means you have to reverse the reaction given to you. Make the reactant the product and make the product the reactant. And when this happens, the sign of the enthalpy changes to become negative. If it's positive, it becomes negative. If it's negative before, it becomes positive. Then B says multiplying the reaction by a constant factor. So you have to check the mole ratio, the number of moles on the main reaction and the number of moles on the given reaction. Number 2, add the manipulated reactions together and cancel out the substances that appear on both sides of the equation. So after the manipulations, correct manipulations, you now add the manipulated equations together and cancel out the substances that appear on both sides of the equations. Then the third is, number 3, add the delta head, the enthalpy values together. Add the enthalpy values of the manipulated reactions to get the enthalpy of the main reaction. So look at some questions now and then apply these steps to solve it. So look at the question on the board that says calculate the enthalpy change delta HF for the formation of 1 mole of strontium carbonate. And you're giving some information, 3 equations on the board. And these 3 equations have different enthalpies. That means when the 3 equations are manipulated and added together, we'll now have the overall equation of formation of strontium carbonate. The overall equation of how strontium carbonate is formed is not given to us. So before we back on this equation, we have to write the equation to show how to form strontium carbonate, 1 mole of strontium carbonate. So to form 1 mole of strontium carbonate, we need, remember that formation how to deal with forming a compound from the constituent elements. So the enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its constituent element. The elements inside this compound are strontium, carbon, and oxygen. So write the equation SR. So the overall equation should be SR plus carbon plus oxygen. to have strontium carbonate. Our concern here is this should be 1 mole. The number of moles of this side can change, but since the compound we're getting is strontium carbonate, so our formation had to do with 1 mole of this. So you make sure that this place is kept as 1 mole. Then balance the equation. To balance it, sodium is 1, carbon is 1, oxygen is 3. To maintain 1 mole here, I need 3/2 on this side. Or 3/2 fraction times 2 gives you 3. So this is the equation for the formation of strontium carbonate. Now let's go to the equations one after the other. Let's look at the first one. Let's look at what are the substances that are in this equation that are in this main equation that I found here. Strontium is found here, oxygen is found there, while these two are not in the main equation. But since strontium is 1 mole here, so and oxygen is half mole, we may think of manipulating oxygen. But if we manipulate oxygen to give you 3 moles, strontium will now change. So there are 2 substances here. So we look at the overall equation, and as I said, if oxygen appear in any other equation, yes, oxygen appeared here as well. But strontium only appeared once. So we keep strontium constant. We don't manipulate oxygen. Since it's 1 mole here and 1 mole there, we take the equation. We don't multiply with anything because strontium appeared only once. Since oxygen appeared in another equation, this can take care of this oxygen. So we'll continue and write Sr plus half oxygen giving us SRO. The enthalpy change is minus 592, as you can see, the kilojoules. So this is 1 mole of strontium and 1 mole also there. So and so is on the right hand side here. Right hand side, this is the same equation. So it's on the right hand side, and also this overall equation. We're comparing to this overall equation. So it's on the right hand side in this given equation, and also on the overall equation. So this equation is in the correct order. Had it been that the strontium appeared on this side, we would have inverted it or reversed it. So strontium is in the same side, on the same side as the overall equation, and then we have 1 more strontium, and also they have the same 1 more strontium here. Not minding that oxygen is different. I kept oxygen like that because oxygen is found under equation. Let's go to equation 2. Compare equation 2 to overall equation. Which substance is found in equation 2 that is in the main overall equation? Strontium carbonate is found in equation 2 and also in the main equation. How many moles each? 1 mole and 1 mole each. Are they on the same side? Product side, yes. So they are the same side and not the same number of moles. So you don't have to reverse this equation. You see, write it down. SRO plus CO2 giving us SrCO3. The enthalpy change is minus 234. You see that? So let's take this thing up a little and then go through it very well. The main equation is this one here. Sr plus carbon plus 3, 1.5, 3/2 moles of oxygen. That is the one we are looking for, the enthalpy of formation. Then equation 1, Sr plus oxygen. So as I told you, what you do is, in each of the equation, check which substance is in the equation that is found in the overall equation. Strontium is here, strontium. Oxygen is there, oxygen is there. Then sodium is 1 mole, correct? Oxygen is 3.5 mole, but half mole. So we are tempted to change oxygen. But why we kept oxygen like that is because oxygen is found in the 3rd equation. It's appearing in a different place. But strontium is appeared only in the 1st equation. So leave it like that. You go to the 2nd equation, strontium oxide plus CO2 giving you strontium carbonate. Delta H2 is minus 234. If you look at this 2nd equation, which substance is found here, that is the main equation, is strontium carbonate. And they both are on the product side. So you're not reversing. 1 mole is correct. You go to the 3rd equation. The 3rd equation is C plus O2. Which substance is in the 3rd equation that is the main equation? Oxygen and also oxygen there. So you have it. You now have C plus O2 giving you CO2. So delta H3 gives us minus 394. And the question is this. The oxygen here is 3/2 mole. Here is only 1 mole. So why didn't I change the oxygen, multiply this by 3/2 all through? Because I did not alter the oxygen in the first equation. So I made it constant. So in the third equation, I still make it constant. I will not touch it. Because having I touched this place will be altered. So strotion was not touched. And I kept oxygen because strotion did not appear. Look at strotion, did not appear in any of these three equations again. But because oxygen appeared in a second place, I kept this place constant. Why I kept this one constant. So this one oxygen constant, sorry, and also this one should be kept constant as well. Since if this was not touched, this will not be touched. So to confirm whether we are right, what I'm going to do is I'm going to add these three equations to see whether I'm going to get this. If I don't get this, that means I'm wrong. I'll go back and manipulate the equation again. So how do we add? Well, first of all, check the substance that on both sides. Look at sodium oxide here and here. They'll cancel out. Look at CO2 here and also there. They will cancel out. You are now left with strontium plus carbon. Half plus 1 is 1.5, which is 3/2 oxygen, giving us the remaining strontium carbonate. So this equation is exactly the overall equation. So how do I now get the enthalpy of formation of the overall equation? That is delta HF. The enthalpy of formation now becomes the sum of enthalpy of the first one plus one plus the third one. Their enthalpy is added all together. That becomes minus 592 plus minus 234 plus minus 394. That gives us minus 592 minus 234 and then minus 394. Our final answer to this question will become negative minus 1220. So minus 1220 kilojoule per mole. So take another question on this Hen's law. So let's look at the problem on the board that says calculate the heat energy evolved from the combustion of 1 mole of ethanol. We have 1 mole of ethanol plus 3 moles of oxygen, giving us 2 moles of CO2 and 3 moles of steam. We're looking for the enthalpy of combustion of ethanol. Remember that enthalpy of combustion is the amount of heat evolved when 1 mole of a substance burns in oxygen. The substance we are concerned with here is ethanol. So 1 mole of ethanol is burnt in oxygen. So here is 1 mole. So this is what we are concerned with. 1 mole of oxygen ethanol burns in oxygen. Number of moles here doesn't count. But we have to make sure the substance that's burning is 1 mole. And we're giving this information. So we're giving the overall equation and we're giving these other steps. I use it to combine. We're supposed to combine this to get that. Let's start with the first equation. In the first equation, you see that the substance that is present here in the first equation that is inside this, the overall is ethanol. We also have oxygen present. So ethanol is on the product side here, but on the reactant side for this one. So what we'll do, we're going to reverse this reaction, reverse it so that the ethanol will now appear on the right-hand side. We're going to modify equation 1. So you reverse equation 1. You reverse equation 1, you now have C2H5. That is this one coming on the right-hand side, giving us 2C plus 3 hydrogen molecule plus half oxygen. And when you reverse, as I told you, the enthalpy sign reverses. Negative will now turn to positive 277.7, no longer minus 277. So changes. You reverse equation 1. And then you look at how many moles of ethanol. You have 1 mole of ethanol here. I have 1 mole of ethanol here. That is balanced. But oxygen appears to be 3 moles here and half mole. So I will not touch oxygen. Why won't I multiply for oxygen? Because oxygen appeared in all the equations. So these numbers can counter this number here. So we're now go to equation 2. For equation 2, you see that the substance is present here. That is present there is oxygen and CO2. Oxygen and CO2 present. Are they on the right side? Oxygen is on the right-hand side. Right-hand side, that is correct. CO2 is on product side, that is correct. But I will go to multiply by any factor for the sake of, not for the sake of oxygen, because it appeared in more than one different equation, so keep oxygen constant. But CO2 appeared only once. There's no CO2 here, and there's no CO2 there. So CO2 is going to be affected because it appeared only once. So multiply CO2 by 2, since there are 2 moles here. So multiply equation 2. Equation 2 multiplied by 2 to make CO2 to be equal to 2 moles. You now have 2C plus 2 oxygen. So multiply by 2, giving us 2 CO2. And the enthalpy change now will change. It will no longer be minus 393. It's going to be minus 393.5 times 2 because of the factor. You use the multiplication. Multiply by 2, you have going to have minus 787. So that gives you minus 787 kilojoules for this one. Then go to equation 3. Look at equation 3. You see that equation 3 is also let's look at the substances present in equation 3. That's in equation 1. Oxygen is there and steam is also there. But oxygen is kept constant. We're not affecting oxygen because oxygen appeared in more than one equation, but steam appeared only in once here. And the number of moles of steam is 3. So what do? We're going to multiply equation 3 by 3. So you now have 3 hydrogen plus 3 over 2 oxygen, you know, 3 steam. The enthalpy change, delta H3 now becomes 3 times minus 285.8. 3 times negative 285.8, and that will give us, the value, let's get it right, minus 857.4. Minus 857.4. So let me go to this process again. What you do is you compare you match or compare the given equation to the main equation. Look for the substance that is present in the given equation that is in the main equation. Check whether they're on the same side. Ethanol is here and ethanol is there. Ethanol is the main substance which you want to find is heat of combustion. So it appeared on the product side here and it's on the right hand side. You have to reverse the equation. You turn it so the product comes this side, and then this one move, the reactant move to the product side, so it will look like the main equation. Then it's not only ethanol that is present here, oxygen is also present here, but oxygen is 3 moles here and half mole. So I would have said, let me look for a number to multiply this half, which could be 6. Look for it to make this half to be equal to 3. But I did not do that. Why? Because oxygen appeared in more than one place. More than one place. So you can see oxygen here, here, and there. So you don't touch it. You see that? Then you go to equation 2. The equation 2 is in correct order. CO2 is on product side, CO2 on product side. Oxygen is here and oxygen is there. Remember that oxygen appeared more than once. So we kept oxygen constant. We didn't multiply with anything. Our constant is on CO2. There's 2 moles here. Multiply everything by 2 to make CO2 2 moles. Good. Although indirectly is affecting oxygen, but our constant is on CO2. Look at equation 3. Water or steam is on product side, also on the product side this side. And there are 3 moles of steam here. Even though we have oxygen, but we're not concerned in changing oxygen because it appeared more than 1 times. So we're going to look at steam. There are 3 moles here. We multiply everything by 3. You have this. So let's bring all this up and see what we're going to do. Bring them up. We'll have I'll clean this one, but I can get it from the manuscript. The first one I have what I have even. I have C2H5OH, giving me 2C plus 3H2 plus half oxygen, and the enthalpy is 277. After reversing it, the sign changes to positive. Second one is 2C plus 2 oxygen, 2 CO2. The new enthalpy change becomes minus 7/8 after multiplying by 2. The third one is 3H2 plus 3/2 oxygen, giving us 3H2O. And the becomes minus 857.4 after multiplying by 3. So when you have done that, the next thing is, let us now add the equations to make sure that this equation agrees with the main equation. If not, we have to change something. So let's see what we can add. Let's find the solder that appear on both sides. You can see hydrogen appeared here and appeared up there. Hydrogen can cancel out. Then let's see, carbon appeared here and also appeared there. Carbon cancels out. So let us add C2H5OH plus, we're going to add this oxygen plus this 1.5 plus 2, that gives us 3.5. 1.5 plus 2, that gives you 3.5, or 7/2 oxygen, giving us 2CO2 plus 3H2O. So that's the equation. Let's see what is wrong. It appears that this one is 3. What is wrong with this? Let's check very well. One of them should be wrong. Oxygen here is 2 times 2, 4. So let's check that something should be wrong somewhere. So let's verify our mistake. Okay, I've seen the mistake here. Look at oxygen here. There's no mistake. Oxygen is here. No mistake, no oversight. Oxygen is here, which would not bring down. So this becomes plus 0.5 oxygen. That is half oxygen will come down. And then if you collect like terms, you now have C2H5OH. So as we said before, entropy is the degree of randomness or disorderliness of a chemical system. So entropy tends to increase in a spontaneous process. So if the change in entropy is more than zero, greater than 0, the process is irreversible and leads to an increase in disorder. But if the change in entropy is equal to 0, the process is reversible and there is no net increase in disorder. We can calculate the entropy of a system by the formula delta S system equal to Q over T. Q over T. So we can calculate entropy of a system by that formula. So let's take equation. So let's look at the equation on the board. For a system at 300 Kelvin, 600 joules of heat is added reversibly. Calculate the change in entropy. So for this question, the temperature is 300 Kelvin. Our heat is 600 joules. Look for the change in entropy. The change in entropy is going to be given by Q over T, which is 600 over 300. And that will give us 2 joule per Kelvin. As simple as that. So at this point, we want to look at the relationship between 4 major thermodynamic quantities: the change in Gibbs energy, the enthalpy change or heat of reaction, the temperature in Kelvin, and then the change in entropy. So the two are connected by this equation. The change in Gibbs energy is equal to the enthalpy change minus the product of temperature in Kelvin times our change in entropy. So what is the importance of the value of delta G? So delta G has the important value in chemistry. If the value of delta G is positive, if this is positive, that means that this change in enthalpy should be more than the product of these two. That is, the change in enthalpy is greater than this multiplied by that. Because if you put the value here, this should be larger than this for it to have a positive value. It means that the reaction is non-spontaneous or not feasible. So any reaction that is non-spontaneous means that reaction is not taking place. Any reaction that is not taking place will have a positive value of delta G, meaning it's not spontaneous, it's not feasible. Now, when the value of delta G is negative, what does it imply? It means that the enthalpy change should be less than the product of these two. So this value should be smaller than these two for it to have negative value. So the enthalpy change is less than temperature times entropy change. The reaction is said to be spontaneous or feasible. So for a reaction to occur in chemistry, the value of delta G must be negative for it to take place. Then when delta G is 0, so if this is 0, that means these two are equal to each other. So the enthalpy change is equal to the product of temperature times entropy change. The reaction is said to be in a state of dynamic equilibrium, that is irreversible, and in a state of dynamic equilibrium. So let's look at the reaction on the whiteboard that says the following data were generated from a given reaction at 25 degrees Celsius. The enthalpy change 0.4 kilojoule per mole. The entropy change 0.5 joule per mole per Kelvin. Calculate the Gibbs free energy and predict the spontaneity of the reaction. If you go to the equation, we're given the temperature, 25, convert to Kelvin by adding 273, that give you 298 Kelvin. You're given the entropy change, which is 0.5 joule mole per Kelvin, Given the enthalpy change, 0.4 kilojoule per mole. You look at the units are not corresponding. This is joule, this is kilojoule. You have to convert this. Unless you have kilojoule and kilojoule here, it can work. Or the two of them are bearing joule, it can work. So you bring this one to joule, or you bring this one to kilojoule. Let's convert this one. One will be 0.4 times 1000, giving us 400 joule per mole, because 1 kilojoule is equal to 1000 joules. So having done that, we can write the upper side and then work. So having done that, we now have the Gibbs free energy again by delta G, delta H minus T delta S. Make our substitution. The value of your G, delta H enthalpy is 400 joule per mole, minus temperature 298 Kelvin, entropy change 0.5 joule per mole Kelvin. So Kelvin cancels Kelvin, and then I'm left with joule per mole plus uniform. So delta G becomes 400 joule per mole minus multiply, have 149.5 joule per mole. So when you solve, or when you subtract the two values, the answer you're going to get is going to be 250.5. Positive answer, 250.5 joule per mole. And you have to predict whether the reaction is spontaneous or not. Because the value of this is positive, the reaction is non-spontaneous or not feasible. It cannot take place. If it's negative, you can say it will take place, or if it's negative, very negative, we would have said spontaneous or feasible. So that is it. So we have come to the end of this topic, chemical thermodynamics for first year and A-level students. So thank you for your time listening to this lecture, or this all-inclusive lecture that took our time. Thank you for your time and your patience. Listen to this lecture. Share our videos to students in your department, in WhatsApp group of students in other higher institutions. Students that need this video, you share it out. Make sure you get subscribed to the channel. Tap on the subscription button. The video is playing. The subscription bell located near under the video. You have the subscription bell. Tap on it, and then subscribe to the channel. Thank you for your time. Thank you very much.